It's time to the afternoon session. I'm Takashi Tsuboi. I was here until 5 years ago. And then now the speaker is Professor Henri Berestycki from École normale des études, École des hautes études sciences sociales et CNRS. And he will talk about the influence of domain shape on propagation in reaction-diffusion equations. So please.
Thank you very much. So well, it's a great pleasure to be here, and I'm really delighted to take part in this inaugural conference of this joint lab between CNRS and University of Tokyo, which is really very natural institution to build. And for me in particular, I have many wonderful recollections of my visits here. So I would like to start with a few personal recollections before I go into the mathematical part of my talk. And the first, so for me, the visits here have always been extremely happy events and very productive events as well, but also very happy events. And I would like to recall just one time when my younger daughter, Noemi, came with me, and we stayed actually in the guest house of this university for a long visit. And that was a very important time in her life, because it really, after that, she changed her attitude towards studying. She found that being a student here was really a very fun thing to do, enjoyable thing to do. So she decided that she would become a good student after that. And so this was part of the events. We were with Professor Matano here. It's on just outside the door here. And the young lady here is Professor Nakamura, who is now a professor in the university somewhere, was then a doctoral student here, and she took care sometime of Noemi. And Noemi actually, she liked it so much that she came back to be a student here. Last year she was a student for 1 year here. And I also remember, I have a particularly nice memory of something we did. It was summertime, and there was this ceremony on the terrace called, there was this game called Sukiawari. Is that? Suikawari, which is watermelon slicing with when you're blindfolded. I tried it and I was miserable, but she succeeded. It was she was very happy to have been able to do that. So that was very nice memories. But I want to say that I'm going to talk about reaction-diffusion equations. So reaction-diffusion equations, there is a very long tradition of collaboration between France and Japan in this field, in reaction-diffusion equations, and the CNRS in particular has played a very important role, and a lot of it also took place here, was organized here. So these are the programs which have been ongoing essentially without discontinuity since 2003. First there was a PEAKS programs and International Laboratory, and GDR. Those are acronyms. French love acronyms. So you have all these acronyms here. I will not go into the detail. First of all, I'm not sure I know them. But anyway, so the last one is taking place actually in the larger network that also involves Korea and Taiwan, actually. So there's been a very long tradition of reaction-diffusion equations. And on a personal note, for me, the first time I came to Japan was at the invitation of the late Professor Mimura, who organized together with Professor Nishida, organized the Taniguchi Symposium. Taniguchi Symposium were really extraordinary events, quite extraordinary events, where we spent a month, in a secluded area, more or less, near Lake Biwa, and we really that was the start of many friendships and lifelong friendship and collaboration. So this was quite extraordinary. Let me just say that you may not recognize me, but I'm on this picture. But also, so here's Professor Matano, Professor Mimura, Jim Keener, Professor Nishida you don't see. Here's Mr. Taniguchi. This is Ito, famous Ito, Paul Five, and that's me. And somewhere Maida, Andy Maida is also here on this picture. So that was really the beginning of this, and that was the time I met particular Mayan Mimura, whom I would like to recall here because he had an important influence. So he was a professor here at this university, and he passed away 3 years ago. And he really loved France. He eventually loved France. He was not loved at first sight at the beginning, but anyways, he really insisted on developing ties with France. He really liked it a lot, and he was beyond some of these collaboration programs I mentioned before. And also in terms of mathematics, he really had a strong influence on the field by developing applied analysis towards mathematical biology. So proving theorems, but also getting, by theorems, by doing real mathematical analysis and getting an insight into the biological phenomena. So, so I was influenced by him also, and so I'd like to recall that this interaction really played an important game. Here's talking about this field. You have a picture with Maya Mimura, Philip Maini, Jim Murray, myself, Daniel Hilhorst, and Hiroshi Matano. Daniel Hilhorst, who's a CNRS researcher at Orsay, played an important role in working for these collaboration programs all along. This was taken in Sergi Pontoise in 2001. So let me start. So I want to talk to you about, since I mentioned Matano, let me start about this discussion about the influence of the shape, domain shape, by recalling a very beautiful result that Hiroshi Matano, who was here, proved when he was still a student. And this result is very general result, very beautiful result, that says if you look at a semilinear elliptic equation, so here is what I call here. So these are stationary states of reaction-diffusion equations. This equation in a domain omega. Omega is bounded and smooth. And you look at Neumann boundary condition on the boundary. So this result says, which actually derived in 1977, I believe, but published then, says that if you take an arbitrary function C1, and omega bounded smooth convex domain, convex important, that any stable solution of this equation must be constant. Very beautiful result, and quite an amazing result, in fact. Okay, and it was also proved at that time independently by Kasten and Holland. So it's a classical result. But Matano went further also. He also proved in the same paper the counterexample, and this counterexample became very useful to construct many other types of solutions. It's really this what people call dumbbell or hourglass or weight, alter in French. So which, if you consider such a domain with a narrow passage here, so this is epsilon is small, then if epsilon is small enough, you can find stable solutions of this equation which satisfies the Neumann boundary conditions, which are near one equilibrium state 1 in one side, and near 0 on the other side, and a small transition here, a smooth transition between 1 and 0. So that's quite striking to see that the result, the convexity is really, you cannot get away completely of convexity. You can try to generalize it, but you cannot get away completely of it. So that was this result. So that's the first result I wanted to recall about influence of domain shape on solutions. So so I'm going to talk about, so this was for general F, but I'm going to talk about a specific class of problems which are called bistable. So the nonlinearities I'm going to consider are of this kind. F is a function of this kind. It has two stable zeros. Stable refers, I will say what I meant by stable in the statement before later on. But here stable just means, you know, that f prime of 0 is negative, f prime of 1 is negative. Think of the dynamical system x dot equals f of x. So those are two stable zeros, and then this intermediate point theta, let me call it theta here. this intermediate point is unstable. And this type of models, this type of equations, like delta u equal plus f of u equal to 0, arises in many contexts. So in ecology, it's really an important, very important type of model. It's related to what people call the Allais effect. So the Allais effect says that if you have think of u as a density of population. So density of population is growth in general by reproduction. It's limited by saturation here in 1. It also diffuses through Brownian diffusion because of the Laplacian term. But if the density drops below a certain threshold level theta, then the effect is adverse to the population. And there are many populations which are like that. For instance, populations of individuals which are subject to sexual reproduction. So if the density gets below a certain level, there is not enough random mating to guarantee that the population will increase. But there are many phase transitions, and as an example, many situations of phase transitions are modeled by something like that. In particular, one of our motives here was a model for spreading cortical depressions. Those are depolarization waves of neurons in the brain. And again, there's this effect that if your density is below a certain level, you go back to 0, but above another level goes to 1, and you want to understand how this thing spreads. So there are many reasons to look at problems with bistable nonlinearities. So what is known here, if you look at the homogeneous equation, there's a traveling front solution, so a solution which is one-dimensional if you want, planar traveling front, which is a solution of this. So you just look for a solution of this kind, and so it satisfies this ordinary differential equation. It goes from 1 to 0. Those are fronts. They propagate with the direction e with an asymptotic speed of propagation, ec, and c has the sign of the integral of 0 to 1 of f. And I'm going to assume that this is always the case, so there will be invasion of 0 by 1. 1 is more stable than 0. And this was proved, the existence uniqueness of phi and c is a very classical result of Fife and MacLeod. So this was homogeneous. So I'm going to talk about non-homogeneous equations. So there's a lot of effort in understanding how inhomogeneity can affect this type of phenomena. Inhomogeneity can come in different ways. It can arise because the equation has coefficients or properties which vary from place to place and time to time, for instance, like this. Or also, another feature of homogeneity was related to the fact that it was posed in Rn. So here, if you pose this in the domain omega, then the problem is not anymore homogeneous in the sense that you don't have these traveling fronts. So for instance, I'm interested in particular here. I'm going to describe situations where you have invasions in domains which varies the width, for instance, varies as you go along x1. And this was the case for the polarization waves in the brain, because in the brain, one of the questions that was asked in the brain was, how does the tortuosity of the gray matter in the brain affect the possibility to have these waves propagate or not? That was one of the questions. So we're going to, and one of the questions is to understand why in the brain these waves propagate in one direction but not in the other direction. And I would like to explain this with these models. So we're going to talk about this non-homogeneous geometry, and I'm going to investigate here first. I'm going to talk essentially about the Neumann boundary condition. So the first result is says that in this situation you can still have the notion of traveling wave, traveling front, albeit not in the same simple way as before, but there is something which is the same role, plays the same role as traveling front. These are called what we call generalized traveling front, or general transition front, even more precisely. So these are solutions which exist for all time between 0 and 1, so, and increasing in time t. And so there is a global solution, and this solution will converge to some limiting state, which I'm going to call u infinity of x. And we'll discuss this in a minute. By the way, all what I'm telling you about the cylindrical type domains is joint work with Juliette Bourse and Guillemette Chapuisat from Aix-Marseille. Okay, so the existence of such solutions follows earlier work that we did with François Hamel and Hiroshi Matano, And with François Hamel, we studied in almost an abstract way this notion of generalized transition wave. I'm not going to talk about that here. And what I want to say here is that the properties of U infinity characterize what I call invasion, propagation, or blocking. So I say there will be an invasion when U infinity is 1. If everything will converge to 1, in the end, like what happens for planar transition fronts, I would say there will be invasion. If, on the contrary, U infinity goes to 0 at infinity, U infinity is positive, but it goes to 0, it means that the wave is blocked. It cannot go beyond a certain barrier. And you can talk also about partial invasion as the same, complete or partial invasion. And you'll see that this depends strongly on the properties of omega, the shape of omega. So complete invasion means U infinity is identically 1. So the first result is that in a narrowing cylinder, if you propagate in the direction where the cylinder becomes narrower and narrower, then there is always complete invasion. So if you assume that okay, omega is a cylinder on the left here, I should have said that before, and it converges to a cylinder on the right, and it's decreasing, it becomes narrower, meaning that at each point of the boundary, the first component of the outward normal derivative is less than or equal to 0. It's greater than or equal to 0. Okay, so then in this case, you can see that U will converge to 1 everywhere, so U infinity, there will be complete invasion, and there will be an asymptotic speed of propagation which is going to be exactly the same as what you see in the plane. So what does it mean, asymptotic speed of propagation? Means that if I run with the speed gamma, and if I take gamma above c, then after a while what I see around me will be 0. If I run with the speed gamma less than c, after a while I only see the state 1. So when these two things happen, I call c the asymptotic speed of spreading. And so this c is a unique speed of traveling front in the plane. It's the same as what you have here. So in narrowing cylinder, there's complete invasion. You recover the speed that you start with, but there's some distortion in between, but you do converge like that. Okay. Okay, so I want to show you this example of narrowing cylinders. These computations were done by Juliette. I think it will work. Okay, so you see this wave propagating. There is nothing happens. Right? There is some distortion when it passes through the passage, but essentially nothing happens. Let me sketch the proof. Now, let me look at the opposite situation. The situation when the domain widens all of a sudden. So you look into a domain, you want to look for each from left to right. In the previous case, we looked from right to left if you want, but here we look from left to right. And we're in a situation where there is an abrupt opening here coming from a tunnel, from a channel which is here on the left. And so the result is that if this transition, say between -1 and 0 here, if this transition is small in measure, then there is blocking. So that is, you will have convergence of the wave to a stationary solution U infinity, which is going to have a limit 0 as x1 goes to plus infinity. So if you go into widening cylinder, abrupt opening like here, there will be blocking. So this is done, all these results are done by essentially using super solution and sub-solution, as is always the case, is often the case, I should say, in parabolic equations. And what's important here is that nothing varies on the right, it's on the left, right, that the incoming cylinder, that's what is small in measure. So here's an example. So you see, I'm going to show you this incoming wave from below is going, and there's an abrupt opening here. And try to see what's happening here. You see, the wave is blocked. Does anyone know why it's blocked, by the way? Why was it not blocked before? Why is it blocked here? It's a very natural question. So let me give you the explanation. Okay. So remember that this describes, for instance, populations which are subject to a Lie effect. So when the density is small, there is an adverse effect of the population. So when the population arrives here, all the individuals who were constrained in this small, narrow channel all of a sudden get access to freedom to roam in a big space. So they become, drunk with freedom, if you want, and they go by Brownian motion all over the place here, but the density drops. So they go all over the place, they are very happy, but they don't reproduce anymore. And the wave is blocked here. So that's the explanation. And you can see on the computation, and this we can prove exactly. Okay, so this is the way we construct a super solution. It's basically you want to construct a solution which is going to be like something that impairs the solution of. You want to construct something like a wall that goes to 0 at infinity that keeps solution under it. And the way you do that is to construct a solution of this equation on, say, on the right here, which is 1 here. So it's going to it's going to be above u. And you take first 0 here for r, and then you let r go to infinity. And the reason is that you can construct that is basically you can find a minimization solution or something like that. Okay, so that's basically what you do, and the reason you can do that is because this is going to be a very small portion. So you can. So, when 1 is a local minimum, 0 is a local minimum, if the channel is small enough, you keep this structure of local minimum and global minimum, and you can just, make a small patch that connects them. So these are solutions which are blocked, the examples of blocking in various geometries. All these are blocking solutions. Now, you can also prove that if the solution, if the transition is gradual, so if there's a small perturbation, let's say, then a small perturbation leads always to complete invasion. So this is a statement which is here. It says if you perturb from a straight cylinder and you make the perturbation small enough, there will be always complete invasion. So this is a result which is here. And I'm not going to describe it more in detail. So here are examples of gradual transition again, and you can see here what's happening here. You see, you get it's slowed down when it goes here but there's enough. It's gradual enough so that the density increases gradually, and it's enough to get invasion. You can understand this picture that if I were to put this angle bigger here, then there would be a critical angle beyond which there will be blocking. Right? If this is the angle which is here, and this is by the way not proved. Mathematics is not yet proved. But it's very conceivable. When the angle, what is known is that when the angle is small enough, there will be blocking. The angle, I mean the angle with respect to the horizontal axis. Okay, and so another theorem that you can prove is that no matter how wide, so it's not a question of ratio between the incoming channel and the outgoing domain. Even if you go into all of space, if the incoming channel is big enough, it's really a relation between f, the nonlinearity, and the width of the incoming channel. So in particular, if the incoming channel is large enough and contains a cylinder of width r, then there will be always invasion. And this is so there will be always at least partial invasion. And this is done by sliding method. I'm not going to describe this here, but basically, as soon as you can slide a sub-solution in your domain, you can have this solution slid all the way to infinity. So it would guarantee that at infinity it will not be 0. And the question is, in this case, the question is, can you? So okay, you know that when the incoming domain contains a channel like that, which is wide enough, so there is a critical size R0. By the way, the fact that there is unique critical size also remains to be proved. But okay, when R0 is large enough, then you know that there will be partial invasion. The question is, under which conditions can you say that U will be identically 1? Can you say that? Can you always say that to the right it will be identically 1? Okay, what do you think, by the way? Is it always 1? Identically 1. So let me give you some. So it would not be fun if it was always 1, because my lecture would be over. But before I go to this question, let me show you what's happening when you have a cylinder which is wide enough. In computation, this is what happens. And you see there is enough, this population regroups here, because there is enough of it to create a secondary source here that propagates from there. That's a phenomenon. So here is an example of that leads to complete invasion. This is a condition. For instance, if you say that you assume two things, you assume that the domain is widening. So this is first component of the normal derivative less than or equal to 0 everywhere. So the domain is widening. And furthermore, you assume that to the right far enough, the domain is convex and unbounded. So this is the type of domain you have, right? So you have this incoming large enough, I say, and then you assume that it's increasing, widening, and that after a certain part, it's convex and increasing. So this is actually, this type of result is in fact, the convexity is in fact, we could see this as an extension to this case of the result I mentioned before by Matano or by Kasten and Holland. It's really on the same flavor. We use convexity in this case. And okay, and so this is done by sliding. Let me forget about this. So it's done by sliding. I'm not going to describe it. But then there is another result. So you may have other conditions that guarantee that the invasion is complete. So one condition, another shape condition, is to say, okay, again, the domain contains sufficiently large cylinder inside. Assume that it's bounded in the vertical direction y, and assume that it's star-shaped with respect to the x-axis. So namely, that at every slice x1 equals constant, it is star-shaped. That's what I mean, okay? So that's one condition. The way you can write it is this way, okay? Again, I assume that it contains a straight cylinder, and that at every, so that's a different condition than convexity, of course. But I assume that it's star-shaped with respect to the x1 axis. Then again, the invasion is complete, and this is done by what we call a sliding cylinder method, which relies on the maximum principle and variance of this. So these are domains which are like that, right? So this is a domain which is star-shaped. This also satisfies the first assumption I mentioned, but this one does not. The assumption of convexity, that assumption of convexity is satisfied here, but not here. And here you have the assumption of star being star-shaped. And okay, so my question is this one. Do you think that the result is always true? Now that we have all these domains, you can, what do you think? Do you think that there will always be complete invasion? After all, no, it's not only me who has to work, right? What do you think? Shall we take a vote? Well, there's a simple counterexample here. The counterexample is what we learned from Professor Matano here. If you put a dumbbell here somewhere, you attach a dumbbell here, you can do the same construction as before. Basically, you can have something which is going to be essentially 0 here, and one there is going to be stable. And so the invasion never takes place here in this pocket. So you see, the role of the shape assumptions on either convexity or star-shapedness is really is not just easy. It's not easy to make our life easy. It's really needed, something like that's really needed, because in those cases, here doesn't satisfy, but here, and if the entrance is narrow enough, you're going to have the same phenomenon, that you will not have complete invasion. So let me just say that to conclude here, two things. The first one is that we have also studied with François Hamel and Hiroshi Matano other situations where the domain shape comes into effect for invasion and propagation. And in particular, one of the things we are interested in is to study propagation through wave passing an obstacle. So in all of space, we studied first the case of a single compact obstacle and tried to understand how you have a wave. That's where we devised our method to prove the existence of generalized traveling front. So you can have a traveling front, pass the obstacles, there is complete invasion, but you want to know, but the invasion may not be complete. In fact, we also had there, so for a single obstacle, we also had some condition. For instance, when the obstacle is star-shaped, then we can prove that the invasion is complete. That's another type of geometric situation. But we also proved that if you have an obstacle which does something like that, the invasion is not complete. In other words, you may have a wave coming in, but never entering this, because there is this narrow passage again. So you have again conditions on the shape. So that was the case what we studied for a single obstacle, compact obstacle. But we are now completing a work where we study passage through a wall of obstacles, periodic wall of obstacles, like what is done here. And there are conditions, again, where you guarantee either complete invasion or, well, there's, again, construction of an invading wave. But there is also a condition that tells you that if the passage is large enough, there will be complete invasion. And if the passages are narrow, there will be blocking phenomena as before. So again, we have these conditions here. Okay, so this is about all what I discussed up to now concern propagation of waves in problems with Neumann boundary condition, du by d nu equal to 0. It's very natural to look at the effect of Dirichlet boundary conditions. Dirichlet boundary conditions are interesting because they pose another type of difficulty. At the boundary, you can think of individuals, if you have a population, you can think that at the boundary individuals are killed or just disappear. So then you have a competition in your equation. You have a competition not only because of the f of u being positive somewhere and negative somewhere, but also because of the boundary effect that is killing in this case, right? So the boundary, for instance, when the domain is too small, you cannot have solutions because the boundary has too much of an effect in this case, if you take a bounded small domain. So the question we were interested in for bistable equations, but that's a general question. The question we were interested in was to study the effect of what can you say about uniqueness of solutions of this Dirichlet problem. It's a very natural question, and again, Dirichlet conditions are very natural to study. So what can you say? When can you say that the positive bounded solution is unique? That's a general question, and this has bears on consequences on what's the large time behavior of these evolution equations. Now, this actually, we started to work with this with Cole Graham, who was an NSF postdoc at Brown University. We started to work on this for positive f. So we started with what's called KPP type nonlinearities, and for which we proved a generic result of uniqueness for KPP. But then we studied very general domains, very general positive nonlinearities f. And for this we use some spectral conditions which allow us to prove uniqueness in many cases. That was for positive F. But what I presented here are, I recall, are bistable, which are like that, not positive. And the question is, when can you say that there is uniqueness for this problem? So to start with, as I said before, existence, if the domain is small, if you take a bounded domain which is small, you don't have existence. That's clearly very easy to see. Again, it's the fact that u equal to 0 is just there's too much, the domain is every point is too close to the boundary for a solution to persist. And on the contrary, if the domain is large enough, you will have solutions. What is known in this case is the old result of Paul Rabinowitz and several others. I had proved it also, but I realized that Paul Rabinowitz had done it before, that in a general domain, in general domain you don't have uniqueness. In fact, what you can expect is that you will have, as you put, for instance, a parameter lambda in front of f of u, as lambda is positive, it increases from 0 solution to, for one value of lambda you have one solution, and then you always have two solutions, one stable, one unstable solution. And so in general, for positive domain, there is no uniqueness, right? So the question is, what can you say about unbounded domains? Can you also say something about the number of solutions in unbounded domains? And so here are some results we proved very recently. It's ongoing work really for this. Is the following result. So we consider domains bounded by an epigraph. So domains which are of the form x prime bigger than phi of x, xn bigger than phi of x prime, where phi is globally Lipschitz on Rn minus 1. So this is the domain we consider here, phi of x prime will be globally Lipschitz. And this is joint work with Colgram and Juncheng Wei. What we proved is that when phi is bounded from below, then the solution is unique, and it's also stable, and you can prove it converges to 1 at infinity. So there is only one solution when the domain, any epigraph. It's quite surprising to see how in an unbounded domain it's quite different, there's uniqueness. In fact, this result here generalizes an earlier work I had done with Caffarelli and Nierenberg, where we proved an analogous result, but for positive F. It was completely open for bistable F. So it's surprising to see that bistable has the same structure in this case. And in fact, this result is sharp. And in fact, what we proved with Colgram and Juncheng Wei, what we are proving now, is that if you take any domain which contains the complement of a salient cone, so if you take a cone which is, let me do it here. No, it's okay. I think we. If you take a domain omega which contains the complement of such a cone, so this is domain omega is around this, so in particular the cone itself, complement of such a cone itself, then there is infinitely many solutions. And so it's quite striking, right? If you take an epigraph, if the function phi is bounded from below, then if you take any cone in particular, then the solution will be unique. As soon as, for instance, if you take a cone, complement of a cone which is salient, going down like that, then there will be infinitely many solutions. So it's very sharp in this sense. And the construction is quite relies on ideas coming from geometry. This related to Delaunay surfaces and things like that. But okay. Let me also say that this, in fact, has also applications to classical problems. Maybe let me try to do the trick you did the other day. I hope it works. Okay. It does. So it's better than École Polytechnique we heard. Okay. Well, so anyways, so for instance, it bears on classical problems of this kind. So you may think that this solution, the nonlinearity here is f of u is u to the p minus u, or minus mu if you put a mass here, if you want. But actually, if you have a bounded solution of, so the nonlinearity is something like that, right? This is UF in this case. But if you have a solution, a bounded solution of this, somewhere here, it's also a solution of a bistable equation, right? So if the maximum of u is between here and the max of u is here, nothing prevents you from considering it as a solution of some bistable equation by just bending back f to 0. And so you can also embed this into a bistable equation. So, in this case, you see that what we prove in this case for this equation is that there is no solution in any domain which is an epigraph. There is no solution because such a solution would have to converge to this. So it cannot have a maximum which is here. So there is no solution in an epigraph which is bounded from below. But as for this problem, in fact, we prove on the contrary that if you take any domain which contains a complement of such a cone, so if I take such a cone, complement such a cone, so something which is not bounded from below, obviously, then in any such domain there will be infinitely many solutions for this equation. So this is a little bit different from, because you have to build them a little bit differently, but the same construction works for this case. Okay, so with this, I would like, so for this, okay, so with this, I would like to thank you for your attention. Go seisho arigatou gozaimashita.